In part 1 of our exploration of the evolution of low-mass stars, we followed the evolution of a Sun-like star from its birth, landing on the zero-age main sequence, to the point at which it begins building up an inert carbon-oxygen core near the end of the horizontal branch phase, when it's deriving its energy from core helium fusion and a little bit of shell hydrogen fusion. We now look at what happens as this carbon-oxygen core begins to build up and become unstable. With no source of fusion energy to provide enough heat to hold itself up against its own self-gravity, the inert carbon-oxygen core will begin to collapse and heat up. At this phase, the star has three sources of energy: gravitational contraction through the Kelvin-Helmholtz mechanism in the inert carbon-oxygen core, helium fusion in a shell, and hydrogen fusion in a thin shell surrounding that. As we saw during the red giant phase, this situation moves the star out of thermal equilibrium. Now the hydrostatic thermostat is even further out of whack, and as a consequence, the combination of helium shell fusion and hydrogen shell fusion, combined with the steady collapse of the carbon-oxygen core, liberating energy by Kelvin-Helmholtz, produces more energy than the star can radiate away from its surface. This excess energy causes the star's envelope to begin to swell up very rapidly. As it swells up, it cools off, and the star becomes more luminous and redder, growing steadily into a red asymptotic giant branch star. This somewhat recapitulates the behavior that we saw at the end of the core hydrogen fusion stage, in which the sun, or the sun-like star, begins to expand into a red giant. But this is called the red asymptotic giant branch, because it occurs at a slightly higher temperature and a slightly higher luminosity than red giant branch stars. It also happens a lot faster. It takes a star like the Sun about 20 million years to climb the asymptotic giant branch. The star climbs the branch again as the carbon-oxygen core collapses and heats up, dumping the excess energy into the envelope and causing it to swell. This time the star is brighter and a little bit bigger in radius because of the fewer and heavier nuclei now in the carbon-oxygen core. The change in the composition of the core means a change in the behavior of the star. The evolution is extremely rapid, whereas it took a Sun-like star about 1 billion years to climb the giant branch the first time. The second time, it takes only 20 million years. A star like the Sun will become about 3,000 times brighter than it is today, with a 200 times larger radius by the time it reaches the top of the asymptotic giant branch. This growth is extremely dramatic and would consume probably Mercury and might even consume the planet Venus. The helium shell fusion, however, is unstable and begins to drive rapid and in fact quite violent thermal pulsations into the envelope of the star. The reason for this is because helium fusion is extremely temperature sensitive. The helium fusion rate scales like the temperature to the 40th power. A 1% change in temperature causes a factor of 40 increase in the rate of nuclear fusion, or 40% greater. This small change in temperature causes an enormous change in the energy output, and so the helium fusion goes unstable. It suddenly heats up, dumping a lot of energy into the shell, which raises the pressure, which drops the temperature and damps down. So it goes thump, 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 like an unstable gas flame that hasn't yet achieved a steady state. As a consequence, these thermal pulses are driven out into the outer envelope and begin to destabilize the outer envelope. If we watch the star from the outside, it makes extremely rapid excursions across the main sequence, suddenly getting fainter and brighter and fainter and brighter as these unstable pulsations go blasting through the outer envelope. Although this is a relatively slow procedure, it takes about 400,000 years for this stably thermally pulsating asymptotic giant branch to occur. So while it sounds like violence here, I'm going boom, boom, boom in words, bear in mind this is a relatively slow process on a human timescale. These pulsations cause the outer edges of the envelope to begin boiling off of the star in the form of a wind that slowly but surely erodes and blows off the outer envelope. When the Sun reaches the thermally pulsating asymptotic giant branch phase, it's going to lose about 46% of its mass by the time that this 400,000-year pulsation phase has ended. Meanwhile, while the envelope is slowly but surely being blown off by these winds over 400,000 years, the carbon-oxygen core keeps on contracting, collapsing under its own weight. However, as more and more of the envelope is taken off, the pressure is taken off the core, and so the amount of heating is less. As a consequence, for a low-mass star, the carbon-oxygen core never reaches the critical temperature of 600 million degrees Kelvin that it needs to reach in order to ignite carbon fusion. So as a consequence, this is the end of the road for the star. At this point, at the end of the thermally pulsating AGB phase, the core and the envelope physically separate. The carbon-oxygen core is left behind, collapsing, and the outer envelope is pushed off into space. This expanding cast-off envelope is heated by the photons, the hot ultraviolet photons, streaming up off the hot carbon-oxygen core and becomes a planetary nebula. The envelope gas is ionized by the very hot bare carbon-oxygen core, causing this gas to fluoresce very brightly for about 10,000 years. The hot carbon-oxygen core is steadily exposed as this expanding envelope becomes thin and transparent to radiation, and as a consequence, we would see it move very rapidly across the Hertzsprung-Russell diagram from cooler to hotter regions, but at a near constant luminosity, until finally the envelope becomes exposed and the core begins radiating very rapidly. Because there's no source of energy, there's no nuclear fusion, only a little tiny bit of gravitational contraction, a tiny bit of Kelvin-Helmholtz mechanism, the carbon-oxygen core left behind by the low-mass star can no longer make up for its energy losses by contraction, and it begins to cool off and fade out. It simply doesn't have enough energy to maintain its luminosity. And so the evolution of the star, if we watched it tracking across the Hertzsprung-Russell diagram for about 10,000 years, would go from very cool to very, very hot as the bare carbon-oxygen core is exposed, but that carbon-oxygen core would very quickly begin to cool and fade out, dropping in luminosity, and as its temperature declines, becoming redder in color. The planetary nebula is the cast-off envelope of a low-mass star. We see planetary nebulae all over the sky as the remnants of low-mass stellar evolution. If the original star was less than about 1.2 times the mass of the Sun, the nebula will actually dissipate before the carbon-oxygen core becomes hot enough to ionize and light it up. However, if the mass is greater than about 1.2 times the mass of the Sun today, the gas cloud formed from this expanding envelope will be lit up and will appear as one of these beautiful planetary nebulae. These are some of the most beautiful objects in the nighttime sky. They get their name planetary because looked at through a low-power telescope, when they were first discovered in the 18th and 19th centuries, they looked for all the world like a planet, a disk. However, unlike planets, they didn't move from night to night relative to the background stars, but in fact remained fixed, clearly telling us they were actually among the stars. As better telescopes began to be built, for example by William Herschel, he began to see that at the centers of many of these planetary nebulae was a bright star, telling us that something very different was going on. Sadly, because the Sun has only got about one solar mass, it is not going to make a planetary nebula during its final phases. When the 46% of the Sun's envelope is blown away during the thermally pulsating AGB phase, it's going to dissipate long before the carbon-oxygen core becomes hot enough to produce enough ultraviolet radiation to ionize it. For a long time, we thought the Sun would in fact have a brief flowering as a planetary nebula, but sadly, that doesn't appear to be the case. We see planetary nebulae all over the sky, and they take many and very interesting forms. Some, like this planetary nebula over here in the upper left-hand corner, are the simple bubbles you would expect for a spherical ejection of the outer envelope. Other stars don't eject their envelope spherically, but blow it off as a kind of a bipolar outflow. This bipolar outflow is then lit up by the ultraviolet light from the collapsing oxygen core. Sometimes the blow-off occurs in multiple phases. But there's an earlier phase that can be barely visible in this picture, but can be seen from molecular emission in the infrared from the first phase of blow-off. Then there was a massive envelope ejection, followed by a secondary fast wind down in the middle, giving this nebula the appearance of a ring. And indeed, this is the famous Ring Nebula in the constellation of Lyra. And there are many, many other and complex forms that we see. Clearly, this process of envelope ejection can be very complicated, and we don't understand what all of the factors are that lead to the many shapes that are seen in planetary nebulae. So these are an area of active study. The planetary nebula dissipates very rapidly. It only lasts maybe a few times 10,000 years. So these are very short-lived, and indeed we see them at about the frequency we expect for the number of low-mass stars that are formed throughout the Milky Way. But what happens to that hot carbon-oxygen core, spare and exposed, sitting down in the center? Well, as the hot carbon-oxygen core contracts, it starts to become increasingly dense. The matter becomes closer and closer packed together into a smaller and smaller volume. Eventually, it reaches the point that it no longer obeys the ideal gas law. If it always obeyed the ideal gas law, the collapse would continue forever. But when it gets above a certain level of density, the rules change, and a new gas law becomes into play. The interior of the carbon-oxygen core becomes so dense that it forms a degenerate electron gas. At this point, the pressure only depends upon the density and becomes completely independent of the temperature. In the ideal gas law, the pressure depended on the product of the density times the temperature, and so we had a very natural relationship between the pressure, density, and temperature within the star. Now, when it's a degenerate electron gas, the pressure only depends upon the density and doesn't care what the temperature is. So as the core begins to cool off, the pressure stays the same because the pressure doesn't depend on temperature anymore. The degeneracy pressure grows until it becomes into balance with gravity, and it achieves a new state of hydrostatic equilibrium. But now it achieves that state of hydrostatic equilibrium when the core is extremely small, when it is about 1/100th the radius of the Sun, or about the radius of the Earth. Shown in this picture, we see a stabilized carbon-oxygen core held up by electron degeneracy pressure, and the Earth shown to scale. This carbon-oxygen core settles down, it's no longer collapsing, it's now in hydrostatic equilibrium with gravity balanced by degenerate electron pressure, and the core becomes a hot white dwarf star. Those mysterious white dwarfs, those tiny, compact, hot objects down in the lower left-hand corner of the Hertzsprung-Russell diagram, they're the remnant cores left over at the end of a low-mass star's lifetime. At each stage of a low-mass star's life, it uses different energy sources to make up for the energy that is lost to shining. At the beginning, in the pre-main sequence phase, it's getting all of its energy from gravitational contraction from the Kelvin-Helmholtz mechanism. However, when the core gets hot enough, above about 10 million degrees Kelvin, for hydrogen fusion into helium to occur, it settles down onto the main sequence. During the main sequence phase, it gets 100% of its energy from core hydrogen fusion into helium. However, that helium builds up inside the core and is unstable. It is not yet hot enough for fusion to occur, and so the main sequence star gets slowly brighter and slowly a little bit bigger until finally it runs out of core hydrogen fusion. The helium core collapses, the hydrogen fusion is pushed into a shell, and the star swells up into a red giant. During the red giant phase, the energy source is shell hydrogen fusion with a small contribution from gravity, the Kelvin-Helmholtz mechanism. At the top of the red giant branch, the core gets hot enough for helium to fuse into carbon and oxygen, and the star readjusts its external appearance and its internal structure, settling down onto the horizontal branch. Now it's getting its energy from helium core fusion and hydrogen fusion in a shell. No more gravitational contraction is needed. This, however, only lasts for about 100 million years. At the end of the 100 million year lifetime, the carbon-oxygen core begins to steadily build up, causing the core to collapse. We get a little bit of gravitational energy through Kelvin-Helmholtz, and nuclear fusion is shoved into a helium and hydrogen fusion shell. These shells are unstable, and they begin to drive the pulsating AGB phase, eventually ejecting the envelope, leaving behind a white dwarf, which is held up by electron degeneracy pressure. A white dwarf is neither collapsing, so it cannot produce energy by Kelvin-Helmholtz, nor is it able to produce energy by fusion. It has no source of energy at all, except whatever remaining internal heat from its initial few hundred million degree Kelvin state was at the time the carbon-oxygen core began to collapse. And so what we're left with is a small remnant, a fraction of the mass of the star, left behind as a white dwarf with no further source of energy to provide for its luminosity. With no source of energy, but in a state of hydrostatic equilibrium, in which gravity is balanced by electron degeneracy pressure, the star has no other choice but to cool off and fade away into the long night.